Hello everyone, this is Dr. Abdul Pasha. We are in the course of Power System Operation and Control. So here I am going to discuss about a block diagram representation of steam turbines and approximate linear models. So this is a continuation to the case of turbine models, and we discussed in the module 2 about speed governing mechanism. So there we've seen so many blocks associated, and there in the case we discussed about turbine models, and for that extension we are representing how the block diagram will be represented for the particular steam turbine case, and if you made the approximation to that turbine model parameters, then how we can design the linear models. So these are the points we'll cover for this particular topic. So coming to the block diagram representation of turbines and approximate linear models, we are here interested not in the turbine valve positions basically, so but in the power generation, the incremental of power is going to be represented with the delta P. So the change in valve position can be represented with delta X, so which may causes an incremental increase in the turbine power. So that increment is going to be represented with the delta P, and due to which electromechanical interactions are going to be takes place with the generator. So it will result in an increased generator power, that is delta P. Then that may be equivalent to the delta P KMS, means generator incremental loss is going to be neglected here. So this overall mechanism is usually relative to complicated, but it will be particularly to the generator voltage, which will be simultaneously undergoes the wild swing due to major network disturbances. So here at present we can assume that the voltage level is constant and torque variations are very small. So then incremental analysis will give a relatively simple dynamic relationship, so which is existing in between delta X and delta P. So such analysis is going to be reveals that considerable differences are going to be takes place, and which are not only in between the steam turbines, and which are going to be taken place in between hydro turbines. So these are in between the various types like reheat and non-reheat cases. So these are relevant to the steam turbine cases. So therefore transfer function relates the changes in the generated power output with respect to the change in the valve position. So here which is going to be varies with the type of the framework which we are going to be connected. So here we can see the block diagram model in the first case, A block. So that figure in this model, the representing the turbine, which will be going to be characterized by a single gain constant denoted with capital K, and a single time constant capital T. So which is going to be the single stage non-reheat type steam turbine, and a single stage non-reheat type steam turbine in the second block is going to be represented this way. So the first block here is the turbine which is going to be characterized individual with respective blocks. So here the non-reheat type steam turbine is represented with the second block. So likewise what is going to be happen here means the reheat type turbine is going to be maintained usually, and the single stage non-reheat type turbine representing the block diagram means which is a non-reheat type steam turbine. So its transfer function is going to be represented here in the manner of speed control mechanism. So this is the transfer function of the speed control mechanism of the given generator with a non-reheat type steam turbine case. So here the first expression representing the transfer function case of the turbine model, that is Gt of S equals to delta Pt of S by delta Xe of S, which is equivalent to Kt by 1 plus S tau T. So here the input section is given with the fuel, that will be the combination of coal and water, and this block is connected to the boiler case, and the boiler is ready to heat, and it will ready to produce the steam on the next case, and this is connected with one of the chamber called steam inlet valve, and that steam inlet valve is connected to the turbine, and this turbine is taking the steam input case, and it is ready to rotate the generator at constant speed. And likewise the process of model of turbine is going to be taken place. So with this the second block is representing the non-reheat type steam turbine. Here its transfer function is representing in terms of delta Xe of S. So which is going to be the input from the fuel section as coal and water, which is going to generate the steam, and it is represented with the transfer function Kt by 1 plus S tau T, and this is connected to delta Pt of S, which is equals to delta Pg of S. Here the input section containing delta Pc of S with the control variable, that is plus 2 minus, and this control variable is connected to Ksg by 1 plus S tau g, and it is connecting to the delta Xe of S case. So here this block is connected to Kt by 1 plus S tau 1, and this block is connected to delta Pg of S. The path is connected from the input section to the variable case in the manner of 1 by R case, and the return path is connected as in the manner of delta F of S. So likewise it is going to be connected as one of the blocks. Here it is representing the transfer function for speed control mechanism of the generator with a non-reheat type steam turbine case. So here typically the time constant T lies in the range of 0.2 to 2. So on opening the steam valve, the steam flow will not reach the turbine cylinder instantaneously. So here the time delay is experienced in this section in the order of 2 seconds in the steam pipe. So from the expression whatever we consider, the first one Gt of S equals to delta Pt of S by delta Xe of S, which is equals to Kt by 1 plus S tau. So here we have the condition delta Pg of S in terms of Kt by 1 plus S tau 1 with the product of delta Xe of S. Here we consider delta Pt equals to delta Pg. So we can represent the expression whatever we considered as delta Pg of S in terms of Kt by 1 plus S tau T in delta Xe of S. That can be represented by one of the block diagram that we already represented here in the second case. This is the block diagram we represented, and the third model whatever we seen here will represents the linearized model for non-reheat type turbine, which will be the including for controller case and the speed governor mechanism case. With the third figure, whatever we observed in the blocks of Ksg by 1 plus S T tau g with connected by delta Xe of S Kt by 1 plus S tau t, that will be representing the combined transfer function of the turbine and the speed governor mechanism model, which will be connecting as Ksg by Kt by 1 plus S tau Sg into 1 plus S tau t. So here this function as the representation of delta Pg of S, which is equals to Ksg Kt by 1 plus S tau Sg into 1 plus S tau t. So here it is the functionality of delta Pc of S minus 1 by R delta F of S. So in general, it is obtained that the turbine response is very low with the response time of the several seconds. So delta Pc, which is connecting to the blocks, is going to be connected as 1 by 1 plus S tau Sg into 1 plus S tau 1, which is going to be connected to SPG of the connection, and this is taking the reverse path as 1 by R with the change in frequency as delta F. So this will represent the block diagram of the simplified turbine governor system. Here we considered with one more parameter called incremental or small signal for a turbine governor system. So if the command of the incremental signal to be delta P, then it in the steady state we will get delta P equals to K into delta P case, where K product is considered as 1, and the block diagram of figure 3 shown here will representing the case with respect to the conditions whatever we assume. That block diagram in the figure 3 reduced that in the another figure. That means this block diagram gives the derivation of an incremental or small signal model case. So this will represent the linearity condition of the system. So the model is adapted for a large signals usage by adding a saturation type nonlinear element. So with this, which will introduces the obvious fact that the steam valve must operate between certain limits. So the valve can neither be more open than fully open or nor more closed than fully closed. So these are the preliminary conditions we must assume when we are going to connect to the valve. It should be neither open or nor closed. So this model of the diagram may also be modified to account for reheat cycles in the turbine, and a more accurate representation of the fluid dynamics in the steam inlet pipes are going to be considered in the hydraulic turbines, which is going to be connected to the penstack arrangement. So reheat type of steam turbines which are going to be modern generating units which have reheat type steam turbines as a prime movers for higher thermal efficiency is considered. So we are going to represent one more diagram, that is a two-stage reheat type steam turbine. So that is indicating the various blocks of the reheat type. So in such turbines, steam at high pressure and low temperatures are withdrawn from the turbine at an intermediate stage level. So it is required to the boiler for re-superheating and then reintroduced into the turbine at low pressure case and high temperature case. So this will increases the overall thermal efficiency, and mostly two factors are going to be influenced the dynamic response of a reheat type steam turbine system. So here the first consideration is entrained steam between the inlet steam valve and the first state of the turbine. And the second state of the condition indicating that the storage action in the reheater which causes the output of the lower pressure stage. So that should be lag behind that of the high pressure stage case. So this is the two-stage reheat type of the steam turbine system. Here it is connected with the input section with the steam valve. Here steam valve is going to produce more steam with the combustion of the chamber, and it will generate high pressures, and this will representing the block high pressure stage block. It is connected to the L pressure, that means low pressure stage block. So these are both coupled by one of the section called reheater section. This makes the reheating of the chambers either sides of the system, that is high pressure stage and low pressure stage cases. And thus in this case the turbine transfer function is characterized by two time constants. So it involves an additional time lag T, which is going to be associated with the reheater in addition to the turbine time constant T. So hence turbine transfer function will be of a second order, and it is given by Gt of S function. So that is delta Pg of S by delta Xc of S, which is equals to Kt by 1 plus S tau T. So this is 1 plus S Kt tau T by 1 plus S tau T. So this is the representation usually. And the time constant whatever we consider T has a value which is ranging from 10 seconds and which will approximate to the time delay for charging the reheat section, and which is to the boiler connected, where K is a reheat coefficient and it is equals to the proportion of the torque developed, amount of torque developed in the high pressure section, which is of the turbine case particularly, which is K equals to 1 minus fraction of the steam reheated. So when there is no reheat, that is K equals to 1, and the transfer function reduces to a single time constant given in that will be considered in the expression. Then transfer functions which are represented in the two expressions gives the good representation within the first 20 seconds of the following incremental disturbances. That means they do not account for the slower boiler dynamics. That means to get an easy analyzation, it can be assumed that the prime mover or turbine is modeled by single equivalent time constant. That means represented with a T that we already represented in the block diagram case. Now another model called generator load model. This plays a key role in the turbine sections. So here in the generator load model, it gives the relation between the changes in the frequency. So change in frequency is represented with the delta F. So as a result of this change in frequency, the change in generation, that is delta P, when the load changes by a small amount, with the delta P is going to be takes place. So when neglecting the change in the generator loss, that is delta P equals to delta P, that is the change in turbine power output, then net surplus amount power, that means total power at the bus bar is delta P minus delta P is going to be exist. So this surplus power can be absorbed by the system in two different ways. So here the first one is by increasing the stored kinetic energy of the generator rotor at a rated level, with W be the stored kinetic energy before the disturbance under normal speed conditions and frequency case. So and W be the kinetic energy when the frequency is F plus delta F, since the stored kinetic energy is proportional to the square of the speed and the frequency is proportional to the one of the speed constant. So here are the expressions which are related to the load model case, that is kinetic energy, which is the ratio WKE by WKE naught with F naught plus delta F by F naught whole square, and one of the another constant WKE equals to WKE naught into F naught plus delta F by F naught whole square. So this is one expression that we already discussed in the earlier section. And another kinetic energy with as the coefficient is considered with the product WKE naught into 1 plus 2 delta F by F naught plus higher order terms are going to be considered here. So neglecting to the higher order terms, then delta F by F naught is small. So this kinetic energy is approximately equivalent to the WKE naught into 1 plus 2 delta F by F naught. So differentiating this term with respect to the T case, we will get dWKE by dt, which is equivalent to 2WKE naught by F naught into d by dt of delta F. So this much of change in frequency is considered. So here let H be the inertia constant of the generator, which is considered in megawatt second to the mega MVA case, and Px, the rating of the turbo generator, is MVA case. Then WKE naught equals to H into PR into megawatts of seconds or MJ. Then equation can be represented, this one, that is a dW by dt equals to 2WKE naught by F naught into d by dt into dt, can be represented becomes dWE by dt, which is equals to 2HPR by F naught into d by dt of delta P, which is represented with one of the equations 7.23. So here the second condition is representing the load on the motors is going to be increases or hikes with the increase in the speed. So load is going to be increases with the increase in speed case. So load on the system being the mostly motor load, hence some portions of the total power is absorbed by the motor load. So rate of change of the load with respect to the frequency can be regarded as nearly constant for small changes in frequency case. So this representation is dou PD by dou F into delta F, which is B delta F, which is one of the expressions 7.24. So here the second condition, load on the motor increase in speed means load on the system being the mostly motor load. So hence some portions of the total power is absorbed by the motor loads itself. So rate of change of load with respect to the frequency is already considered here as regards to the nearly constant for small changes in frequency. So this change becomes delta Pg minus delta Pd, that is dWKE by dt plus dou Pd by dou F into delta F. So with the expressions of 2324, then above modified expression can be represented here as delta Pg minus delta Pd equals to 2 HPT by F naught into d by dt of delta f plus b delta f quotient. So dividing throughout by p of the expression, we will get delta pg of per unit value minus delta pd of per unit value. So which is being the equivalent to 2h by f naught into d by dt of delta f, which is aiding to the b of per unit system in delta f, and taking the Laplace transformations on both the sides, then we will get delta pg of s minus delta pd of s, which is equivalent to the constant 2h by f naught s into delta f of s plus b delta f of s. So this may be the coefficient equals to the 2h by f naught of s plus b into delta f of s. So therefore delta f of s equals to delta pg of s minus delta pd of s by 2h by f naught into s plus b, which is equivalent to 1 by b of delta pg of s minus pd of s by 1 plus 2h b f naught of s. So which is equivalent to kps by 1 plus tau ps into delta pg of s minus delta pd of s. So this is represented with equation 7. And here the parameters tau ps equals to 2h by bf naught is the power system time constant. Normally we considered it for 20 seconds. And kps equals to 1 by b. So the power system gain which will representing the equation can be represented in a block diagram model with earlier figure we represented. So the overall block diagram of the isolated power system is obtained by combining the individual blocks of the speed governor system for a given turbine model, and a speed generator load model is shown in the figure. So which is the representation being a third order system, then the characteristic equation for the whole system will be of the case of third order case. So likewise we can make the entire system in the third order module system. So this is the actual block diagram presentation for a generator load model. So that is delta PD of S, which is connected with one of the generating system delta PG of S. So this is the entire control block which is going to be controlled over two parameters. So that is delta PG of S and delta PD of S. So these two blocks are connected to the one of the control block KPS by 1 plus S tau PS. So which is connecting to the one of the change in frequency of the system as a function delta f of s. This is the block diagram representation of the generator load model system. So here the various aspects are considered for the generator load model, even though the system parameters are considered with the change of frequency. Here the power system time constant will plays a key role. That means the specified time limits are considered for a period of 20 seconds, means this will be divided with the one of the coefficient called B, that is a power system gain with the KPS, that can be represented in the block diagram means. So this will make the system gain for the whole of the network. So likewise the parameters whatever we assumed are considered in the various blocks are associated with the system. So they may ready to works with the consideration of the PG of S and the PD of S systems, and they are going to be changes with respect to the frequency parameters. And whatever the load model considerations we considered as the parameters, these are going to be treated as one of the constant parameters with respect to the power system gain. And they may gradually changes to the change in frequency case, and this third order system will be connected to the characteristic expression for the whole system. So this whole system is going to be connected with these parameters as the respective blocks are associated here. So this will represent the complete block diagram for the isolated power system when it is connected by the generator load model. This is connected by delta PC of S, which is going to be tied to KSG by 1 plus S tau SG case, and it is connecting to delta XC of S with KT by 1 plus S tau T. And this block is again connected to delta PG of S with one of the control variable by delta PD of S. And this block is connecting to KPS by 1 plus S tau PS, which is as a function of delta F of S. The return path here is connected to the 1 by R block. So this is the one of the return path we are connecting into the system. So this complete block representing isolated power system means whatever the variables or parameters we connected here are is going to take one of the complete positions of the system. So this makes the system to make entire operating of the system. So with respect to these parameters, Xe of S and one of the Pg of S, PD of S coefficient, the whole of the network may going to be changes. That means the whole parameter as a function of frequency as a delta FFS is connected to the return path of 1 by n. So this will makes again to simulate the network for given input case for various ranges of the output. So these frequent operations are going to be takes place for the entire power system network to the specified time period limit. So this will makes the system to be stable and they are going to ready to operate for various conditions. Likewise, this will ready to operate. And these are the references which I have selected for making this presentation smooth. And thank you.
Like, share and subscribe. Hit the bell icon for more updates.